Hey, it's Tony from Adafruit, or is it Spark Industries, or Stark Industries? Oh, I screwed that up, uh-oh. Anyways, though, so you can see I'm in my cosplay for Emerald City Comic Con. This is Tony Stark from Stark Industries, Avengers, Iron Man. So I've built an arc reactor right here, and this arc reactor, the one that I'm actually wearing, is powered by Circuit Playground. So that's our all-in-one little electronics learning board. It has some NeoPixels around it, and then I put an extra ring of NeoPixels around it that you can see light up and do some cool animations. Now this is using the classic version of Circuit Playground, which is the ATmega 32U4 microprocessor. Same thing you find in Arduino Leonardo or most of your Arduino boards. You program it with the Arduino IDE. But there's a new version of this board coming out pretty soon, and this is actually a version of the arc reactor I built. So this is the ring of NeoPixels on the outside, and then this purple board in the middle is actually a prototype of the Circuit Playground Express, or that might not be the final name, but it's a board that is like Circuit Playground, so it's got NeoPixel sensors and things integrated into it, but it has the SAMD21 microprocessor, which is a more powerful version of the processors that you can find in Arduinos. It's the same processor as used in the Arduino Zero, and with that you can run Python or CircuitPython, which is a version of MicroPython that we've ported over to run on this processor and simplify a little bit so it's easier for beginners to use. I've done a whole bunch of videos on MicroPython and CircuitPython, and in this video I wanted to focus on how I took this Arduino sketch, which is powering the animation of these NeoPixels, and converted it to run in CircuitPython. And I'll actually show you it runs on the same hardware, just with that fancier, better little Circuit Playground Express board that runs Python. So the big difference is this one I'm wearing right here is programmed with Arduino, so you've got to use the Arduino IDE, you're limited to what it can do, whereas this one right here we're going to program with Python, with CircuitPython, and it's really cool. You will interactively kind of develop this, and I'll show you some issues and things I ran into as I converted this sketch over to run on this board. And real quickly, I'll give a quick little demo. This is actually more than just a static set of animations, because on Circuit Playground there are two buttons, there's a slide switch, there's a light sensor, there's a sound sensor, there's a little buzzer. So I've added some level of interactivity to this. It's basically, when this runs, it will every 15 seconds pick a random color, and there's a set of colors, gradients of colors actually, like there's a primary and a secondary color, but it'll pick a random color every 15 seconds, and then every 30 seconds it'll pick a random animation, and there are 4 different types of animations. But if I press some of the buttons on here, like this right button, this will actually change the type of animation. So this is the chase animation, where it's just doing a sine wave with the color gradient, but it looks like it's kind of chasing, around the pixels. If I go to the next animation, this one I like a lot. This one's really cool. This one is the heartbeat animation. So you can see it's kind of like ba-boom, ba-boom. So it's like a heartbeat kind of animation where the inner pixel will flash, the ring of pixels, and then the outer ring of pixels will flash after it. And you can see it looks really neat with the different colors and things on it. So you can see it just changed colors after 15 seconds. So that's kind of a fun one. If I press the left button, this will cycle through different colors. So this is going to, some of the colors I have go from like a primary color down to black. And so you're seeing like this is like a pinkish color down to black. But this one, this is like red to cyan kind of colors here. Okay, so that's the heartbeat animation. And then I also have, this is the sparkle animation I call it, where it's just randomly lighting up each of the pixels between the primary and the secondary colors. So it gives this kind of neat computery random effect, because I figured, hey, Tony Stark, he's got the arc reactor. Why does it have to be that cyan color? Let's light it up. Let's make it fun and interesting. And so that's what I've done with my arc reactor here, or my power reactor. Okay, and then the last animation here, this is just a glow animation where you can see it just fades in and fades out. So just a nice pulsing kind of animation. But this does change based on the colors. So if I cycle through all the primary colors here, we'll get to eventually some of the gradients, like, oh, almost there, I think. There we go. So you can see it goes to color gradient. This goes from cyan to red. So kind of a neat effect. And then I've got all kinds of other color gradients in here. I basically took every primary, I looked at the color wheel and picked the primary colors and secondary colors and did kind of those combinations and adjacent colors and things. So there's about like 20 or so color combinations you can do. And so that's kind of cool. You can press the buttons to cycle through these and maybe pick an animation. But then if you don't do anything after 15 seconds or so, it's just going to go through and start picking random animations. Because when I go to Emerald City Comic-Con tomorrow, it's going to be March 4th, actually. Tomorrow I'll be at Emerald City Comic-Con in Seattle. I'm going to be wearing this, obviously, and doing this cosplay. And so I want this to be going through kind of interesting and exciting animations for it. And there's one last thing that this does. There's a little slide switch on Circuit Playground, basically a little switch that you can move into a left or a right position. And if I move that slide switch, then it basically turns it off. And on this version of the sketch, it's actually putting the processor into deep sleep mode. It turns off the NeoPixels. So it tries to pull as little power as possible because I do have a little lithium-ion battery. It's behind my shirt right here that's powering this whole thing. And there are a lot of pixels here. There's 24, or actually 34 pixels total. There's 10 pixels on the inner ring and 24 pixels on the outer ring. So when all of those are lit up, that can pull a decent amount of current. I was actually measuring it with my bench supply, and it can pull about 0.5 amp of current. So that's a lot of current for something that you're wearing. But then if I slide that switch back into the other position, it will turn back on. So you can see it just jumps back to life like that. So it's kind of cool. It's nice that, okay, if I step into an elevator or something and maybe I need to be more subdued and hide my true identity, I can turn off my arc reactor like this. So, okay, so let's get started. What I'm going to do is, like I mentioned, so I have an Arduino sketch that I already wrote ahead of time where I just wanted to prototype these animations and play around with it. It was a little more familiar to me and faster. I'll walk through real fast the hardware. It's very simple to build this, and I'll have a guide on this in the future. I just haven't had time to put it together yet. But I'll walk through the Arduino sketch really briefly, and then the meat of this, I want to get into how I converted that Arduino sketch to run on CircuitPython. And so this will hopefully be a useful video because this is a non-trivial sketch. You can see, this has 4 different types of animation, 20 different colors or so, interactivity with different buttons, so different button presses cycle through different animations. So this is not just a blink and LED sketch. This is actually a pretty advanced sketch, and I'll show you how I converted that into CircuitPython, and then we'll probably touch on a few performance issues and things I ran into as I did that conversion. Because remember, the big difference with MicroPython and CircuitPython is that you can run Python code on these boards, but it's not as fast and it's not as efficient as the code that runs on your Arduino, because that's compiled down to the machine language code, whereas Python code is interpreted by the CPU on here. So there's some overhead to that. But we'll see that we can get pretty darn similar performance between these. And actually here, I'll plug this in. It's running the sketch right now, so I can just demonstrate that it's pretty close to the same level of performance as this version of the board. So you can see this is doing the glow animation. And actually, there is a weird little quirk. Here, let me plug this in with a battery. Because when I plug this in, sometimes it gets noise on the USB port, and then that actually will accidentally send a Control-C command, which tells the board to stop running. And that's why you see it sometimes glitch out when it's plugged in like that. So if you see weird issues like that, it doesn't happen when I power it by a battery, though. So just real briefly, I will plug in the battery here, and then we can see, okay, so you can see this is doing the glow animation like I've shown before. Nice, smooth glow animation. If I press this button, now it switches to, this is the chase animation, so you can see it's going through the different colors. And it's a little hard to tell. It actually looks pretty smooth, but it is a little bit slower than this version of the board, and we'll see why later as I get into more of the details around this. This is the heartbeat animation, so I really like this one. And actually, this heartbeat animation is a little bit different than this heartbeat animation. So if I switch to it, let me see if I can find it again. I think it's the 3rd animation. Yeah, there we go. So you can see these are the heartbeat animations. So this one, you might notice, it doesn't go completely black. And I think that's because the math that CircuitPython is doing is actually floating point math, whereas I'm doing fixed point math. And so you get a little better math with this. It's slower, unfortunately, CircuitPython, but that's a trade-off. Anyways, let's see. So the heartbeat animation, here's the sparkle animation, which is kind of the random. This is doing blue and green kind of colors right now. But it also has, I can change the colors. So it's a little hard to tell because this is so bright. I guess I could put this, I don't want to put it under the shirt right now, but you know, you get the basic idea. So this is doing that kind of random animation, and then this is the glow animation again. So same behavior, and if I flip this slide switch, it turns off like that. Now it's not going into deep sleep, but I actually measured the current, and the current consumption, even when it's just spinning in a loop for the SAMD21 board, is pretty close to the same current consumption as this board in deep sleep, which is kind of funny to me. So it's, you know, even though it's not the most efficient, it's still reasonably power efficient. It's pulling about 27 milliamps of current, which is a lot of current for something in sleep, but this thing pulls 18 milliamps. It's got this little LED on it and stuff, so it's not the most power efficient thing in the world. Anyways, though, I can flip it back on and turn it on, and we're good to go with this. So again, this one is running Python, this one is running Arduino code, and we'll look at how to convert to this Python code in a moment here. So let me put this away, put this battery away just so the cat doesn't get to it, because she's in her feisty wants to play mode right now. So anything with little wires could be a problem. Okay, so let's go to the main view, and we'll start looking at the code for this. Let me switch here. Okay, there's the main view, and let's put the hardware here. And maybe real fast, before I get too far into this, let's jump to the workbench view instead first. There we go. So I'll just show, oops, oh boy, that's a little wild. Picture in picture, there we go. So real briefly, I'll just show the hardware. So like I said, this is the Circuit Playground Express board, which is not out yet, but this is a version of Circuit Playground, which is like this board, right? Oh, actually, this is also a Circuit Playground Express board. This is an early prototype. This is a later prototype. I think this one's going to be pretty close to the finished board. There may be a few more tweaks and things, but I should have. Here is a classic Circuit Playground, and so this is. You can see there's not much difference between these. So this one has the ATmega 32U4. That is this big processor right here, and then this one has that SAMD21, which is this processor right here. On here. And then you might also notice there's this extra chip right here that might, like right on my fingernail. That's a little SPI flash. So there's an extra bit of flash memory on here for storing your Python programs. Whereas on your classic Circuit Playground, you just have that ATmega chip because it can't run the Python code here. Everything else is pretty much the same though. I mean, you've got your accelerometer, your buttons, your slide switch, all that stuff is here. Anyways though, for my power reactor, my arc reactor, I just put a ring of 24 neopixels outside of it, and the nice thing is it fits exactly. So this ring of neopixels has an inner diameter of 2.1 inches, and Circuit Playground boards, both the classic and the express ones, have a diameter of 2 inches. So you've got a 0.1 inch clearance, just enough clearance to let it fit, and it actually has a little bit of play inside of there, which is nice. Now what I did, this is actually a name tag magnet that I put on the back. Let me pull this thing off. So you can see it's just a little magnet, and I've clipped it to my undershirt here basically. So that's how I've got it affixed to my shirt. And then all that I did was just soldered some wires. So this NeoPixel ring, it has a power input, it has a ground input, and it has a data input. So the power input I've connected to the VBAT line of the Circuit Playground. That gives you your battery voltage, so whatever battery you plug in, it will output it there. The other option is the 3.3 volt output, which I think is right here, but you don't want to use that because that's the right voltage that these pixels, technically I think the pixels want 5 volts, but most of them run off of 3.3. Although that's the right voltage, that goes through the voltage regulator on the Circuit Playground board, which can only support, I can't remember the exact number, but probably less than 500 milliamps. And again, when all these pixels light up, they can pull a lot of current. So the VBAT line is connected directly to the battery, so it gets 3.7 volts from there. And the nice thing is it can pull as much current as your battery can source. So a little lithium polymer battery can provide a lot of current. And so you're basically going to power your pixels directly off your battery, which is what you want to do, because if you try to go through that regulator, you might pull too much current and the voltage will drop, the board will stop working, maybe you can fry something. So, you know, be careful about that. The ground connection, though, is really simple. I've just connected it to one of the ground pins, or not really pins, but kind of connectors on the outside of Circuit Playground right here. I've just soldered a wire on there. And then the data input line, this needs to go to any digital input. I've connected it to the SCL pin, or pin number 3, just because it was next to the pin right here. Now I did leave a little bit of a loop of wire, and the one important thing here too is you probably want to use solid core wiring instead of stranded core wiring, because you can see the solid core wiring, I can hold this by the ring and it's nice and solid, and the inside circuit playground doesn't move around. You know, it keeps everything kind of tightly held together. If I use stranded core wiring, the circuit playground inside would flop around, like there would be nothing supporting it. So I'm using these wires kind of as support to hold the ring to it. And then I left a little bit of excess. So you can see like I have a little bit of a loop here. I mean, I could have gone directly from this ground pin straight over to the ground wire right there and kept it really tight and small. But I left a little loop here, and that's so that I can actually move this around a little bit, because I want to get to the programming port right here. And if I had it connected like this, you can see the outer pixel ring might block it. But by adding a little bit of extra play in all of the wire connections, I can move this. So you can see I can kind of tilt this out like this, and I can plug something in. You know, it gives me a little bit of extra play so that I can move this around and get to all the components. So I would recommend doing that if you're building something like this. You know, use solid core wiring and add a little bit of extra length to it so that you can move it around. And you can see, I mean, this thing, it's nice and held kind of tightly in place by the wires like that. So that's the hardware. It's that simple. I mean, you're just connecting a strip of NeoPixels to the circuit playgrounds. It's not too intense, but it's you do want to think through, again, you know, how you build that. Okay, so let's jump back to the main view again with the code and things. Okay, so that's the hardware, and again, this is the CircuitPython version of the code. I will go through real briefly the Arduino sketch for this, and then I'll also show that I put this code up on GitHub, and I'll put a link when this goes up on YouTube. Look in the description below, and there'll be a link to this GitHub repository, so you can see the code in this repository. And I have both the Arduino sketch and the CircuitPython code inside of here. So you can look at both of these and kind of see, again, the whole point of this video, I want to kind of look at how to convert from Arduino code to CircuitPython code and look at some of the advantages and disadvantages and trade-offs of that. Okay, so the Arduino sketch, I'll real briefly go through this. This is a bit of an advanced Arduino sketch, so you might see some things that you haven't seen in a lot of Arduino sketches. Just because it's kind of a style I like to take with more advanced sketches. I like to break things out. Oh, there's the cat. Yeah, I told you she wants to play right now, so who knows? It's a live internet, so anything can happen here. Anyways, though, so the first thing you might notice is I've got all these tabs at the top, and what I've done is instead of putting all of my code in a single file, I broke it out so that I put things into separate files. Because this is a relatively complex sketch, and so it's easier for me to put things in separate files so that it's a smaller file to look at. You know, I don't have to look at this giant 2,000 line file. I can look at, okay, there's a file with all of my animations, this animations.h file. There's a file with all of my colors defined inside of it, the colors.cpp and .h. This reactor.h defines some global kind of classes that I created to abstract away some of the complexities of this sketch. So that's what you might notice at first, and you might not even realize you can do that in Arduino, and it's this little button right here. You can create a new file, you create a new tab basically, and that file just lives next to your .ino file in your sketch. So it's, and if you're familiar with like C and C++, this isn't anything new to you, but it is kind of cool that Arduino lets you do this. Okay, so I put, like in most sketches that I do, I like to put, oh boy, my cat's meowing now. I like to put a lot of configuration at the top, so this is like some values that you can tweak. So you can tweak like the brightness of the NeoPixels. Right now this is on full brightness, and so you can see behind the shirt it kind of obscures it a little bit, but it still shines through enough to get the point across. There's a color period and a animation period. That's the number of seconds that it will stay in a certain color or animation before it switches to the next random color or animation. And then the NeoPixel configuration, this just configures which pin is connected to the outer ring and the inner ring of NeoPixels. And then there's also the count of those pixels, and then the type of the pixels, because the NeoPixel library in Arduino is pretty advanced and there are lots of different types of NeoPixels. So this lets you tweak those values. Then I have a bunch of global variables that I won't really get too far into, but the interesting ones are how I define the animations. So what I did, like, and actually maybe I'll scroll down first of all to the main loop function. So you can see this is the main loop function right here, and it looks a little complex, but it's actually not that big. It's kind of generic. Like, the main loop has no idea what the glow animation is, or what the sparkle animation is, or what the chase animation is. That's actually something that I defined in this animations.h. So I made a class for each of my animations, so that way I could abstract away the code and say, okay, there's a generic type of animation which is represented by this animation class, and it by default it doesn't do anything. It just knows that it has to have an update function, and that update function will be called by my main loop. Now what that update function does is up to each implementation of the animation. So the glow animation update is going to be different than the chase animation update or the sparkle or the heartbeat animation update. Each of those update functions implements the actual code to light up all the neopixels. But the generic animation class just knows that it has an update function. It doesn't know what it does. It doesn't care what it does, because that's really all my main loop cares about. So you can see this is where it calls the current animation update. It doesn't need to know that, okay, I'm in the glow mode, I better call the glow animation function. It just knows that there is a current animation that's been selected and I should call its update function and let it do its own thing. And my main loop doesn't need to know or care what that animation function, what that update function does. It's just up to the class, the animation class, to implement that animation update function. So very common thing with the object-oriented program that you see, this kind of abstraction where you can say, okay, I want to implement new behavior in a subclass, and so it's going to implement and override this update function to implement the animation itself. So I define this base class right here, which basically says, okay, there is an update function that can be called, and then each of my animation classes will also get a clock, a pixels, and a colors object. And so these I've defined in the reactor.h header. I've defined a clock object and a pixels object. And again, these are just abstractions. The clock object is just abstracting away the current time, because all of my animations depend on the time. Like in that glow animation, you know, it goes from on to off, and it's using a sine wave to do that. So it needs to know the current time to do that sine wave computation. The chase animation, it's actually using a sine wave to cycle around all the pixels, and again, it needs to know the time for that. Now I could bake into all of my animation classes the code that will read the current time, and maybe some of the animations might need to know how much time has elapsed, whereas other animations might be simpler and just need to know like what is the current time, like the current number of milliseconds or things like that. So rather than have all of that code duplicated across all of my animations, I just made a clock class that just has a concept of what is the current time and what is the current elapsed time. And the elapsed time is how much time elapsed since the last loop iteration. That's a really common thing you see with animation. So I figured I'd put that all into one class so that now in my animation implementations, each animation will have a reference to this clock object. And this is using pointers. Again, this is a little bit of a more advanced Arduino sketch. But each of my animations will have a reference to this clock object, and now when my animation wants to know what is the current time or what is the elapsed time, they don't have to compute that. They just ask the clock, say, clock, give me the elapsed time, give me the current time, and then it's up to the clock class to figure that out. And so that lives in its own bit of code right here. And it's just using the millis function in Arduino. This just returns the number of milliseconds using a millisecond timer that Arduino hardware has. So that's what the clock function does, or class rather. And then the pixels class, like the clock, this is just an abstraction, whereas this abstracts the concept of the outer and inner pixel rings. And so it gives you two different views of those pixel rings. One view is it gives you explicit control over both the outer ring and the inner ring independently. So if I want to light up the inner ring, I can deal with this inner object. And if I want to light up the outer ring, I can deal with the outer object. So that's useful like in the heartbeat animation. Let's see if I can get to that one. Yeah, there's the heartbeat animation. So you can see like in the heartbeat animation, it lights up the inner ring first and then the outer ring. And so it does that by just interacting with those members of this pixels class. But some of the animations don't care about that, and they just care about all of the pixels as a whole. So all 10 of the pixels on the inner ring and then all 24 of the pixels on the outer ring, put those together and you have 34 pixels total. And so that's what I implemented on this class, was a concept of the same functions you find on the NeoPixel class. So things like setting the brightness or setting the color of a pixel or getting the number of pixels. It basically makes both of these rings look like one long neopixel strand. And it just does it by looking at, basically my setPixel function. You give it the index of the pixel you want to set the color of, and you give it the color value. And then it just looks to see, okay, where does that pixel fall? Does it fall within the inner ring? Is it within the first 10 pixels? And then, in that case, I should light up the inner ring of pixels. Or does it fall in the outer 24 pixels? So is it index 10 or beyond? In which case, then we should light up one of the outer pixels and just do a little bit of math to figure out, which pixel I should light up from that outer ring. So again, the pixel class, this just abstracts away common operations against these neopixels that I figured I would have. Because again, I don't want all of my animation code to have to do all this logic. I don't want my animation code to have to know, okay, there are 2 rings of pixels, and my second ring of pixels starts at this index. My inner ring of pixels has this many pixels in it. I don't want all my animation code to know that. I just want my animation code to know, hey, there's this pixel object, and it's got an inner ring and an outer ring. And if you want to light those up, just talk to those objects directly. Don't worry about figuring all that stuff out yourself. All of that logic and junk is abstracted away in this pixels class. So again, it makes my code a little bit simpler, so that now when I go back to this animation code, let's look at, so for example, here's an implementation of the glow animation. That is this animation that's actually playing right now. So this is glowing. It's going between one color and the next color. So in my color class, I have a primary and a secondary color. So it's just using a sine wave to go between those 2 colors. So you can see the implementation of this class. It just fills in that update function right here, and it's pretty darn simple. This is the whole class right here. You can see there's no logic for like dealing with like what is the current time, what is the elapsed time. It's actually just using that clock object, so it's getting the current number of seconds right here, and it's multiplying that by a frequency. And so that's something that's specific to the glow animation. So when you create an implementation or an instance of the glow animation class, you have to tell it what frequency to run at, and that's how fast it transitions between those 2 colors. But it's just using the sine function here. So I'm just doing some sine math. You can look up the sine wave equation in Wikipedia. I think I've shown this a bunch of times in videos. But 2 times pi times your frequency times your current time in seconds will basically give you a signal that goes from +1 to -1 and repeats at the frequency you specify. So a frequency of 1 means once a second it will go from, it actually starts at 0.5, or it starts at 0, goes up to 1, and then goes all the way down to -1, and then goes back up to 0. So you get a nice continuous up down signal at the frequency you specify. But if I change that frequency to like 0.5, that means twice a second it's going to go. So you get a faster frequency in that case for this. So that's nice, and that this makes this animation code really simple, so that I just need to do that sine wave computation. And then once I get that sine wave value that goes between 1 and -1, I just interpolate my color. And so the color class is again another abstraction where basically I made a gradient object, and the gradient is just a color gradient that goes from a primary to a secondary color, like red to blue, and then all of the colors in between there. Oh, looks like the cat, she tired herself out apparently. Anyways, so you get a primary and a secondary color, and the interpolate function just says, okay, I want to get a color in between my primary and secondary color. So, let's say I've got red as the primary and blue as a secondary color. Right in the middle is pink. And so if I want to pick a color in between there, because, as it's doing that animation, let's go back to the glow animation here. Let's see. Oh, that's heartbeat. That's the chase. There we go. So this is the glow animation. So it's glowing from orange to black, orange to black. And so halfway in between there would be like half orange, basically. So that's what this interpolate function does. And the nice thing is you can see my animation code doesn't need to know or care how to interpolate colors. It just knows that there's some gradient object that's been set ahead of time, and it can call this interpolate function, and it can pass it a value. So it passes the output that it gets from the sine wave value, and then it tells it the range. It's just telling the interpolate function that, hey, this value that I'm passing you at one extreme is -1 and at the other extreme is +1. And so it's going to interpolate in between there and pick the color that's proportional to the value you've passed in here. So, when my sine wave gives me a value of like -1 all the way at the bottom, it's going to give me one of the colors, like the primary color, because I've told it that's one of the low values. And then when the sine wave moves up to the +1 value, it's going to give me the secondary color, because I told it that's the other limit. And then when it's in between there, like when it's a value of 0, it's going to give me a color in between my primary and secondary color, like halfway in between exactly for that. So it does the color interpolation in the animation, and then it just fills all my pixels with that color. So that's all that this animation code does. And it's nice that you can see this animation code is really just defining only how to animate this thing. It's not figuring out what the current time is. It's not doing the interpolation. It's letting other classes deal with that. It's abstracted all of that away into these other classes so that you really get to the core of what is this thing. It is an animation, and it should only do this animation logic. Anything else should probably be abstracted away into other classes. So that's the glow animation. The chase animation, this one is basically going through, and it's using a sine wave again, but it goes pixel by pixel, and it will offset the phase of the sine wave depending on the pixel location. So just kind of a fancy way to say that it's, instead of lighting all of the pixels up with the same sine wave, it's basically each of the pixels will see a different position or phase of the sine wave, which makes it look like it's kind of chasing around. And it's, let's see, that's the sparkle animation. Let's see that. So this is the chase animation. So you can see it looks like it's moving, but you're really just seeing that sine wave in motion across all the pixels. So that, if you look at a single pixel, it's just lighting up based on that sine wave, but each pixel is offset in time a little bit so that, the pixel right next to another pixel is a little bit slower or behind the other pixel, so that, one pixel lights up really brightly and the pixel next to it lights up, just half as bright, or not necessarily half as bright, but a little bit less bright. And so you can see that kind of turns into that nice kind of sine wave motion across all the pixels. And so that's why it looks like a sine wave moving across all of these. Okay, got to pick up the pace here. We're about halfway into this video and haven't even gotten to the Python code yet. So anyways, the heartbeat animation, this one, I won't go too far into it, but what I'm doing is I'm using exponential decay. So I was using a sine wave before. Here I'm using exponential decay, so that this is the heartbeat animation. And basically what it's doing is, if you look at the exponential decay function, it's basically at time 0, you get a really high value, off the charts if you're graphing it. And then it falls down very quickly. So you get, time 0, super high value, and then, all the way to like time 1, or at some point in the future, it drops back down dramatically. And that's exactly what you see with this heartbeat, where, your inner ring, let's see, oh, it changed animations already. Let's go back. So here's the heartbeat. So you get that boom, that high value initially, and then it falls off and fades away very quickly. So it's like boom, high value, fade down, high value, fade down. It just does that repeatedly over time. And so that's what I'm doing here. And you use, you take e to the power negative some time constant divided by your period here. Look up exponential decay in Wikipedia. Well, here actually I'll show you, just so I remember to put a link in here. Exponential decay. And you'll see when you look at a graph of this, it makes a little bit more sense as to what I'm doing. So you can see this is a graph of exponential decay, and right here, time 0, really high value, and then it falls down dramatically over time. And it tells you actually how you can compute different values here. So for a discrete set of values, which is kind of what I have here, you can use this equation. That's exactly what I've implemented in my code right here. I'm just using this equation to control the pixel color over time. And I'm interpolating between the primary and the secondary colors based on this. Okay, finally, the sparkle animation. This one just uses a sine wave. And again, it's a sine wave per pixel, like the chase animation. But now, instead of having a frequency for the whole sine wave that's fixed, each pixel is assigned a random frequency. So when I go to the sparkle animation again, so there's the sparkle animation, it looks kind of like things are randomly turning on and off, but what's really happening is each pixel is assigned a random sine wave frequency. So, one pixel might go really fast, primary to secondary colors, and then the pixel right next to it might randomly be like really slow primary to secondary colors. And so when they're all next to each other and all with random frequencies, it gives it this nice random look, but it's organic in that it, you see that kind of ramp up and down from primary to secondary colors instead of just a very discrete like on off, because you could just use the random function and just say if it's above some threshold, set it the primary color, if it's below it, set it the secondary color, but then you'd get this on off, look a little too harsh. So I wanted it to look a little more organic, and so I just kind of thought about it and figured, oh yeah, let's just do sine waves per pixel, random frequencies, and it gave it a really nice effect. So I like the sparkle one a lot. Let's see, yeah, there's sparkle with kind of like a blue or a cyan color for it. So again, that's all that happens in this update function. Now, this one's a little more complex. I have this randomized frequencies function where this will go through and set a random frequency per pixel. It'll save it into an array that it creates, but it's just using the random function right here, and then it's interpolating between a set of frequencies that I set here. So, okay, I'm not going to spend too much more time on this code. The colors, I define this whole list of colors right here. And so this is kind of nice. I can change all these color values. And then in my setup, it's really not too complex. Basically, I initialize my random number generator using the light sensor actually on here, which, oh, actually, no, this, I forgot to update this. The light sensor would be A5. So I can use the light sensor to just give me a random value, and that's going to initialize my random number generator. And then I do my basic circuit playground initialization, serial initialization, initialize the neopixels, set the brightness. And then for all of the animations, because I save my animations in this array of animations right here, and this is actually where I create my animations. So, my glow animation, this is where I set its frequency to like 0.66, and my chase animation, I set its frequency to 1.33. The heartbeat animation, it takes in the beats per minute, and so that's 60 beats per minute. And then the sparkle animation, I need to tell it how many pixels and the range of frequencies to randomly pick between. So that's where I set those values. But when it initializes all of these, it needs to set that pixel and clock object that we saw, because remember in the base class, I have this pixel and clock object in here that each of my animations needs to know about. So I just basically go through each of my animations and tell it, okay, here's a reference to the pixel class, here's a reference to the clock class that I was talking about there. But then in the main loop, so the code is, again, pretty straightforward. This is the part where I check to see if that slide switch is, what position it's in. If it's turned off, I turn off the pixels and I go into deep sleep mode. I'm using the Sleepy Dog library that uses the deep sleep mode of the AVR chip. Then I grab my initial button state, because to detect when the button is released, I need to get an initial state, wait a small amount of time, get a second state, and see if it changed from pressed to not pressed, and then I can tell if a button has been released. Because I don't want it to just cycle through super fast. I don't want to just check has it been pressed. I want to check has it been released, and so I need to tell kind of that change in state. So I need to do 2 measurements for that. So I get my initial button state, then I do all my main update logic right here. So I update my clock because there's one clock object. I need to tell it to update. And then all of my animations read from that clock object. So they'll figure out that, the time has changed or the elapsed time has changed. And then let's see. Then I go through and I set the current color for my current animation. And basically I'm just telling it here is the currently selected color, because when you press the buttons and things, it might change the color. And then I call that update function on my current animation. And so you can see I figure out my current animation by just indexing into my list of animations based on this current animation variable. So this just holds what number animation is currently selected. 0, 1, 2, 3, which animation should I pick? And when I press the button to change animation, I just increment that value, which you'll actually see down below here. So the next bit of code, I have a small delay because I want to debounce. I don't want to just constantly look for button changes. I need to wait a little bit of time to let the button settle. But I get a second button reading, and now I can look and see, okay, if my button, and the way the buttons are set up on Circuit Playground, if you press the button, then it's true, and if you don't press it, it's false. So if I get, basically, I was right the first time. When you press it, it's true. When you release, it's false. So I want to detect when you release. I want to detect when you go from true to false. So your first reading is true, it's pressed, and your second reading is false, the button is released. So it'll detect that exact moment in time when you release the button. And the way to do that, if my initial reading is true and my second reading is false, so that exclamation point negates it and says, okay, this is false, then I know I want to increment my animation. So I just add 1 to my current animation. And then I'm using the modulus operator to just make sure that it, if I go beyond the total number of animations, it wraps back around down to 0. And then I reset the amount of time that I've spent in the current animation and the current color. That's basically because, you see every 15 seconds it changes the color and the animation. But I figured if I pressed a button, I probably want to stay in that animation and that color for a little bit of time so that I can see what I actually did. So I just reset my elapsed time for the current animation and the current color. Same exact thing is done for the color. I look for the right button press and do the exact same logic, but I just change which currently selected color. I just increment that by 1. And then the logic to figure out when I should change to a random color, I just increment how much time have I spent in the current color. That's my elapsed color milliseconds variable here. How much time have I spent in the current animation? That's my elapsed animation milliseconds variable. And again, I just increment it by the delta milliseconds, like how much elapsed time has my clock spent since the previous loop iteration. And this is nice because I don't need to do this computation in my loop. My clock class does that computation automatically for me. And then these 2 little things at the end here are actually doing the check to see, okay, after 15 seconds, or this color period milliseconds, after I've elapsed that amount of time, then change to a random color, and then reset my color, the amount of time I spent in that color. So same exact thing for the animation. After I go 30 seconds and I elapse my animation period, then pick a random animation, just use the random function. This is going to give me a value up to that animation's length. So it's going to give me a random index into the animations, and then make sure to reset the time that you spent in the animation for this. Okay, so that's the sketch. And again, that's a pretty complex sketch. I need a drink of water actually after walking through that whole thing. Okay, so let's see. Let's dive into the CircuitPython version of this. And let's see, I'm thinking I want to keep this within an hour. So I've got 20 minutes left. I don't think I have enough time to write all of this code, but we'll kind of bootstrap this a little bit because like I said, I've already written some of the code. I've written all of the code actually for this. It's on this GitHub repository. So if I go back to this in the CircuitPython folder, there's all the CircuitPython code for this. And you do need to be running the latest version of CircuitPython. This doesn't work with MicroPython. And again, you're probably not going to be doing this right now because you need one of these prototype circuit playgrounds, which aren't in the shop yet. But you could wire this up to a SAMD21 board, and you would need an inner and an outer ring of neopixels, obviously. But this is probably for the future. Once these boards are out, you'll want to look at this. But anyways, let's look at this code. So I'm going to open my editor. So we'll close Arduino IDE. Yes, let's save that because I forgot that I did that light sensor change. Okay, so that's the Arduino sketch. Here is the CircuitPython sketch. And let's see, I'm trying to think, excuse me, how I want to walk through this in 20 minutes. So we could start with the main.py, and then maybe I'll implement the animations. I'll re-implement the animations so that we can see how I did those animation implementations and maybe some of the performance issues that I ran into. Because again, I wanted to kind of focus on some of the differences, and like I did actually run into some performance problems when I was doing this code. So, okay, so here's my main code in CircuitPython, and it's pretty similar to my Arduino code. Like my Arduino code, I separated this out. So I have a main.py. This is my main sketch. I have a reactor.py where I have a pixel class and I have a clock class. And these are exactly like the Arduino classes that I had before. So my clock class, basically I have a current time, current number of seconds, current number of milliseconds, and elapsed number of seconds. I think I called this delta milliseconds in the Arduino class, but I called it elapsed seconds in this class. But it's just using the time.monotonic function in CircuitPython to figure out what is the current time. It's not giving you like, your watch time. It's giving you a counter that will increment once every second, and it actually has floating point accuracy, so you get like millisecond accuracy. But I just use that, and then I multiply that by 1,000 to figure out what's the current time in milliseconds, because some animations might want to look at what's the millisecond time versus what's the second time. And then the elapsed time, I initialize it to 0, but every time I call the update function, I just compute what is my elapsed time based on what was my previous current time, what is my new current time, what's the difference between there, that's the elapsed time that I compute right here, and then I just update all these values like the current time and the current milliseconds for here. So again, the clock class abstracts away all the concepts of the current time and the elapsed time so that my animation code doesn't need to worry about that again. The pixel function, or class rather, just like the Arduino code, this has a concept of an inner pixel ring and an outer pixel ring. So it saves those references as properties that I can manipulate, or I guess attributes of this class. And then I also compute the number of pixels. And so I tried to follow the NeoPixel class. It has a convention where the n property or the n attribute or class member, I forget what it's called in Python. I'm just going to call it attribute for now. But the n attribute is the number of pixels. And so I just say, okay, the total number of pixels is the inner plus the outer ring number of pixels. And then I implement it again like a fill function that fills all of the pixels. Basically this getter and setter function are like the NeoPixel module where you can index into it to set the colors of specific pixels. So this again is the logic that makes this pixels class look like one long strand of NeoPixels, when in reality it's two different strands, the inner and the outer strand of NeoPixels. But this bit of code hides that difference and lets me deal with it as if it was one strand of pixels. We'll come back to this set pixel RGB function. I'll show you what this thing is later. This is a performance optimization that I had to make for this. But again, so that reactor.py is just like the reactor.h in the Arduino code. Same exact concepts. The syntax changes, obviously. And it is kind of nice that this is a lot simpler code. I guess, just to show a direct comparison, like the clock class right here, this thing is 10 lines of code, 11 lines of code maybe, versus if I go back to the Arduino version of this, so here I'll open it in the text editor. If we look at the reactor.h here, here's the clock class. This thing's looking like 20 lines of code roughly, because, in C++, there's a little bit of more cruft and overhead. I wouldn't say cruft, but it's a little more verbose about how you define a class. A lot more curly braces in here. You have to have a constructor, which is the same thing as an initializer in Python. So this is kind of your constructor in the Python world, this initializer function. And then, here's my update function, which I've defined in line right here. And then all of the attributes of the class you have to explicitly define in C and C++. So, I need to tell it there is a current millisecond attribute, and here's the type of this thing. I need to know ahead of time this is an unsigned 32-bit integer. Whereas if I look at the Python version of this, there is no definition for that. Python is dynamic. I can add attributes to this class at will, and that's exactly what this self.currentS does. It creates a currentS attribute on this class. I don't need to know the type. Again, Python's dynamic. I can set this to a number. I can set this to a string. I can set this to another object. Python will figure it out and make it work, whereas in C and C++, I have to be very explicit and tell the compiler, this thing is an integer, and not just an integer, a 32-bit unsigned integer. And again, there's trade-offs. So I'm not going to say that this is better or worse than one way. With this method, the compiler can be smart, and it can know if I write code where I try to set current milliseconds to like a string, it will say, ooh, you can't do that. You're trying to set a number to a string value. I'm going to not even let this compile. Whereas in Python, it's happy to do that. It's just an attribute. An attribute can be anything. It could be a string, it could be a number. So there are trade-offs to that, in that the code is simpler, but you're getting less things done, like less error checks and things done by the compiler. Oh, it looks like the cat, she's interested in the GoPro batteries potentially. So let me pull those away from her. I don't think you want that. There we go. Last thing I need to start eating a GoPro battery. Anyways, so again, if you're not familiar with Python or C and C++ code, hopefully this can kind of help you see some of the differences here. And it's kind of nice. I like in Python how it's so quick and easy to prototype things and just put together simple classes like this without a lot of overhead. Whereas in the C and C++ world, you've got to kind of learn the syntax and, make sure you get this semicolon in here. If you forget this guy, oh, look, see, my editor even knows, like, this is going to cause a giant failure. So it's very prickly and particular about things. But that's because it's trying to help you. It's trying to tell you, like, hey, dummy, don't set a string to this integer value or something like that. So there are trade-offs to that. Anyways, though, so that's what the reactor.py does. The colors.py, I won't get too much into this. I have this whole concept of gamma correction, which is in the Arduino sketch also, where basically the human eyes perceive color differently than the neopixels actually show them. So I guess I should say rather, your eyes see shades of color at different intensities. I think you actually have more blue receptors, I want to say, in your eye, or maybe there are less blue receptors. I forget exactly which one it is, but so a blue color, you would actually see that more intensely at the, with the neopixels, you have an individual red, green, and blue pixel. You set each of those, their intensity values, to a value between 0 and 255. So if I set a blue pixel to 255 and I set the red pixel to 255, your eyes actually see that blue pixel brighter because you have more blue receptors in your eye for that. So that's what this gamma correction thing does, is it actually tries to account for that and fix that nonlinear response between those, between the color intensity values. And it's kind of interesting. Phil B actually has a really good little write-up on this that I stole this code from, so I should mention it here. And if you're kind of curious, search for NeoPixel Gamma Correction. And this is in, like, Phil B gets into all the details around this in this little guide here. And he talks about how to fix this and how to do this in an Arduino sketch. And so that's exactly what I did in my code here. And I'm actually computing this gamma curve in my MicroPython code. I did this for memory reasons because I didn't want to store. So in Phil B's code, he actually shows you in your Arduino sketch, you can put this big lookup table in memory, and then you can use this to very quickly do this gamma curve, this nonlinear response. And then he also shows you in this guide how to generate that code. And so you could actually generate this. It's just using a power function, exponential function, to generate this. But it would be slow to generate that every time you needed a color value. So that's why you build this lookup table. And so I actually build a lookup table here in the MicroPython code, which is kind of cool. And it's the power of MicroPython here is that, I can just do this simple math operation, and it's very easy to read this code and understand it. But again, I have a gradient class, just like we saw before in the Arduino sketch. It has an interpolate function. It has a primary and a secondary color, and it interpolates in between those. And here I got really fancy, and I did this kind of functional style of programming where I'm using the zip function, where you have two iterables, and the zip function gives you a single iterable with a two tuple of both values. This is a little complex. This is just a very complex way of me basically going through each of the color components and calling this linear interpolate function on them all. It's I like to do this style, but it's maybe not the easiest thing for someone new to Python to understand. But it's kind of cool to see how this would work. I mean, ultimately I'm just interpolating between the first, second, and third components of each of these primary and secondary colors. I'm calling this lerp function on those with this crazy block of code right here. Interpolate component, we're going to come back to what this thing is. This is a performance optimization. But here I define all the colors. Now I don't define these in my main.py sketch. I define these in my colors.py because you might notice I have a colors.mpy file in here, and this is a binary file, so it won't actually show anything useful in my text editor. But that's because I've used the mpy cross tool to pre-compile my MicroPython source code. Sorry, I just wanted to see what my cat is doing, make sure she's not getting in any trouble. I think she's debating if she should jump into the box back there, so we'll see what she does. Anyways, though, so I pre-compiled this MicroPython source code into this .mpy file that's more efficient and faster for MicroPython to load into memory. Because I noticed, actually, if I try to define all of this code in my main.py file, it looks like she made the leap, so she's back there in her box. If I put this in my main.py file, I actually run out of memory trying to parse all of this code, because when it's parsing that raw Python source code, again, this is the big difference between Arduino and MicroPython or CircuitPython code, all of this Python code has to be read into memory and then converted into this abstract syntax tree of like bytecode and all of this processing that turns it into executable code. All of that has to happen on the tiny little processor right here. And that processor only has a little bit of memory. I forget how much memory. I think it's, boy, I should remember this. I think it's like 16K memory. It's a small amount of memory on this chip. And so this big list of gradient objects, actually, like the parsing of this took up all of the memory. So the way I fixed that is I put it into its own file, ran this mpy cross tool, which basically does that parsing step ahead of time and outputs this .mpy file, so that now I can copy this colors.mpy file onto my MicroPython board or my CircuitPython board. It can load that file up and it won't have to do that parsing step. It's done ahead of time, saves on memory, and it actually lets me load this file up. So that's why I've defined my colors in this separate file so that I can pre-process it. So again, this is a little performance optimization trick that you're probably going to run into as you convert your code from Arduino to CircuitPython or MicroPython code. Okay, let's see. So neopixel.py, this is the NeoPixel driver code. I've made a special change to it right here, which I'll come back to in a second. But this is, again, a performance optimization. CircuitPlayground.py, this is just an abstraction around the Circuit Playground object or class. Well, I guess hardware, really. This look more for this in the future. We're going to actually make a nice little Circuit Playground library. So I just abstracted away the concept of the NeoPixel ring that's on Circuit Playground, the left button, the right button, and the slide switch. And actually I should put a nice little space in between there. So I just made these global objects so that I can import this Circuit Playground module or .py file basically, and it will just give me those buttons already defined. So, you know, on this hardware, the left button is fixed to the board.left button pin, and so I created an input for it. I basically switched to an input. And for these buttons, you need to set like pull down resistors to make them work the way that you expect. Same thing with the slide switch here. So this just simplifies my main code. So now when I look at my main code, we can kind of see it's very similar to the Arduino sketch. So I have some configuration at the top. I don't have the brightness configuration because the NeoPixel class doesn't have the same concept of brightness. You know, it's full bright, unfortunately. So you don't have brightness control. Sorry. But I do have the same concept of how much time do I spend in a certain color before I move to a random color. How much time do I spend in an animation before I move to an animation? And I could change these. If I wanted to make this, you know, how about 25 seconds? I could do that. Or, you know, if I wanted to do like 22.7 seconds for some reason, I could do that because it's a floating point value. I can just set it to any value like that. So that's nice and simple and easy to change. I also define, here's the pin that's connected to this outer ring of pixels and the number of pixels in this outer ring, just like the Arduino sketch. I set up some global variables just like the Arduino sketch where I have to create that outer ring of neopixels. Then right here I create an instance of my clock and pixels object. So I imported this reactor.py file, which gives me the pixels class and the clock class. And so right here in my main.py, I create an instance of that object. Sometimes I get cat hair on this mouse and it's a little bit annoying. It slows down. So that's where I create an instance of my clock and my pixel object here. So these are just the global variables, just like in the Arduino sketch. Here's where I define my list of animations, and this is where it gets a little bit simpler compared to Arduino. So in the Arduino code, it's pretty crazy. You know, this is where I define my animation list right here. So to make this work in Arduino, I have to define this abstract animation type. You know, this animation base class basically, and then I have to say, okay, now I have an array of pointers to animation objects, and then I make an array of these things and I set it to the pointers to explicit instances of all these objects. Let's look at the Python code. This is much simpler in Python. In Python, it has a concept of a native list object. So that's what I'm creating right here, which can dynamically size itself. So I don't have to fix the size of this thing ahead of time. And it can store anything. It can store objects, it can store numbers. It doesn't care. Everything is an object in Python. So I can just create instances of my animation objects. So in my animation.py file, I have a fade animation, a chase animation, a heartbeat animation, a sparkle animation. And so I just create instances of these. And again, each of these animations just takes in the same parameters, like the frequency for the fade, the frequency for the chase, the beats per minute for the heartbeat, the sparkle animation, the number of pixels, and the frequency range, things like that. So this is where you start to see how much simpler some of this code is. So I'm defining this list of animations. Now I call this underscore animations because when I import this animations module, which imports this animation.py file, which will re-implement this, I think that's what I'm going to have time for in this. This will probably go about an hour and a half. But I can't call this variable animations because I've already imported something called animations, and so these variable names would conflict, and so that actually would cause a problem. The way you get around that usually in Python, or the convention, is you add an underscore in front of things, usually. So if you see that in Python code, that's typically what's happening. Or in a class, underscore typically means this is a private member, although Python has no real concept of private variables. So typically you put an underscore in front of something to say like, hey, don't touch this thing, or if you touch it, do it, it's at your own risk. You might screw up whatever the class creator intended for that. Okay, so I've got the same concept of my current animation. This is just which index, which animation is selected right now as the one that should be shown. Same thing for my colors. Again, though, I defined my colors in the colors.py file so that I get that MPY optimization versus my main.py. I'm not using the MPY cross tool on my main.py, although I probably could if I really wanted to. But I didn't do that, and so that's why I define my colors in a separate file. But I still need to have an index of here's the currently selected color, and here's the amount of time that I've spent in that current color. Okay, so here's kind of where the setup code runs. This is the code that runs first. Well, actually, all of this code above runs first, but this is effectively my Arduino setup code. So it's just some code I'm going to have run once. And then below it, I have a main loop, an infinite loop. And so that's kind of my loop function, because that's another big difference between MicroPython, CircuitPython, and Arduino. In Arduino, you have a setup function and a loop function, and your setup is called once and your loop function is just called repeatedly. Whereas in the Python and MicroPython and CircuitPython world, we don't have that yet. Maybe in the future there might be some frameworks that add that, but you kind of have to do it yourself. So your setup code is just the first code in your .py, your main.py file, and then if you want a main loop, you've got to create it. So you have a while true loop here. But anyways, so this setup code, so I like to make that distinction in my code here, at least, of like, here is where the one-time setup code goes, and then here is where my main loop, my over and over code goes, basically. So in my setup code, I'm basically reading the analog, the light sensor, and using it to seed my random number generator. So in MicroPython, there's the micro random or the urandom module. It has a seed function, and I can pass it a value that it's going to use to seed the random number generator. That just means, because if I didn't do that, the hardware built into your boards here, I'm just checking to make sure it's still working. It still is, luckily. The hardware built in, it doesn't have a hardware random number generator that uses like some interesting entropy source, maybe the cosmic background radiation. It's not that smart. Hey, these chips are only like a few cents. You're not going to get that kind of feature on it. So they use these pseudo random number generators, which have to be given a random value to generate random values. And if you don't give them a random value, you're going to get the exact same set of pseudo random numbers. So if I didn't do this, I would actually get the same cycle of animations and colors over and over. Like every time I powered on the board, it would start with the same cycle of colors and animations, which is probably okay, because if I'm walking around the Comic-Con show floor for hours at a time, no one's going to really notice that, hey, oh, you've been walking for 4 hours and you're on the blue animation. I could predict that. But, the inverse side of this, like why random numbers are so important. Let's say I was using random numbers to generate passwords or something like that. If somebody could guess that string of random numbers, and, if somebody could guess what my pseudo random number generator will generate next, they could guess what passwords I'm going to generate. And that's how a lot of websites get into trouble, because their random number generation is not as random as they expected. And people can guess what random numbers are going to be generated. And if you can guess that, you might be able to guess passwords and things like that. So that's interesting little insight. But so I'm getting around that by seeding my random number generator with a value from the light sensor, which is probably going to be random. I mean, it's going to change depending on how much light is hitting the light sensor. So just depending on how bright the room is when I turn this thing on, that's how it's going to seed the random number generator. Then I just turn off all the pixels, just a good initial state to start in. And then I set up in my animation, we'll come back to this, but basically I save an instance of the clock and pixel object in my animation module so that all of my animations can reference it. And I don't have to go and set this on each animation. So this is how I do that. And we'll come back to this when I implement some of these animations. Now in my main loop, this is exactly like the CircuitPython or the Arduino code. So I do a check to see what's my slide switch value, and you can see this is that Circuit Playground class that I was talking about. So it has a slide switch member inside it. It's not a class, it's actually a module, but there's a global inside there called slide switch. I get the value. If it's turned off, then basically I turn off all of my NeoPixels, and then I just sleep for a small amount of time, and then continue will just do it'll pop out of the while loop and jump back to the start of it again. So it will check and see, is my slide switch still not turned off. So right here is an optimization where it would be nice to have a deep sleep function that turns off the CPU. I thought the cat jumped out of there. But we don't have one yet in MicroPython or CircuitPython, so maybe in the future we'll have a deep sleep. For now, this time.sleep just spins in a loop internally, so it's not really doing anything fancy. But I get my initial button state right here. So this is just like the Arduino sketch. And then I update. So I update my clock just like in the Arduino sketch. I set the currently selected color, and we'll come back to this when I implement the animations. I tell the current animation to run its update logic. So this is where, if the glow animation is selected, it's going to run the update function for the glow animation. If the sparkle animation is selected, it's going to run that one. So that's, exactly like the Arduino code. And then I write out the NeoPixels because my assumption is my animation update function will change the NeoPixels. And then this then right after that, I'll just go and write out the NeoPixels, light them up appropriately. Just making sure that thing's still working. Anyways, then I get a second button press right here. Now notice I don't have a delay, and that's because the MicroPython code is a little bit slower than more than a little bit. It's a lot slower than the Arduino code because it's interpreted. So I don't really need to put a delay in here because this code is slow enough that it's doing that debouncing for me effectively. But I get my second reading, and then I just have the exact same button press logic. So when the left button is released, I increment my current animation. So I add 1 to it and then use the modulus operator to wrap around back to 0 after I get past the total number of animations. And I reset the elapsed amount of time in the current animation and the current color. Same thing for pressing the right button. I change the color. And then I have the exact same logic for incrementing the amount of time I've spent in the current color and the current animation. And then after I elapse that period of time for my color and my animation, I just pick a urandom.random integer. So I pick a random color to choose. And so the urandom.randint function in MicroPython, you give it the range, your minimum value, and then your maximum value. But it gives you a value including that maximum value. So I want to pick the length of my colors array -1 because I don't want to pick the length of my color array because it might actually give me that value, which is going to go 1 beyond the size of the array, and that'll throw an exception in Python. Luckily, in Arduino, it would probably lock up, or you would get undefined behavior if you try to index outside the bounds of an array. Whereas luckily in Python, it'll throw an exception, which just means my arc reactor would stop. It would freeze up. Anyways, so just be careful. Look at the bounds of your functions here. And so this is an inclusive function, which means it will generate a random value between 0 and colors -1, including 0 and colors -1. So that's why I have those values there. So okay, so hopefully you can see this main code is exactly the same as the Arduino sketch right here. And I tried to make it very explicit, like the comments are the same here, all of the logic is the same. It's just slightly different in the syntax. There are curly braces here, whereas there's white space in Python. But it's, the logic is the same. And so again, I'm hoping to get across in this stream that, when you're converting between these two worlds, your code can stay the same. It's just the syntax that really changes. And then in a lot of cases, your syntax gets simpler because you can see things like in Python, it's much easier and faster to create a list of objects with Python syntax versus in Arduino syntax, where you've got to, create these types, and then you've got to create like fixed size arrays, or you've got to use a vector, which is a variable sized array, all this complexity. Whereas in Python, if I want an array of things, I just make, square brackets and list all the things I want, and I can call .append to add new things to them, or I can remove things from them. It's all nice and dynamic. So, okay, so let's get to the meat of this then. Let's re-implement the animations for this. So let's make a new file in here. I'm going to call this animations2.py. And then I'm just going to go through and we'll basically re-implement the glow, the cycle, or sorry, the glow, the chase, the heartbeat and the sparkle animation. And I don't know, maybe I'll start with a few of these and we'll see how much time it takes. And maybe if it takes a little too much time, we'll grab the other animations that I had. So okay, so my animation functions, let's make a class inside of here. We're gonna make a glow class. And just like in Arduino, so if I go to the Arduino code, in my animations, I had this base class. The cool thing is in Python, I don't really have to have a base class, because the only reason I have this is in the C and C++ world, if I have a list of all these animation types, I can't have a list, like it needs to know what is the type. And so, the glow animation is of type glow and the chase animation is of type chase. I can't have an array of both chase and glow objects in C and C++. I can only have an array of the same type of object. And so that's why I have this base class, this animation object, and I can have an array of animation objects, and each of those objects could be a subclass, like a glow object, which inherits from animation. So it is an animation object. But I can't just have a list of glow, chase, sparkle objects or whatever. I have to make this base class. Whereas in Python, I don't have to do that. That's the cool thing. All objects are the same, basically. And when I call a function on an object, Python will look up to see if that function exists on it. So already my code is simplified that I don't need that animation base class. So now I just need a glow class for my glow animation. It needs an initializer, which is kind of your constructor in the Python world. I like to just start by implementing it as an empty function, just will pass and do nothing. And then I'm going to add an update function. And in Python, in all of your class functions, they take in as the first parameter the self object, which is kind of how it references all the properties that are on that object. Okay, so this is where I need to fill in my glow animation logic. So let's go back to the Arduino code, and let's just copy out this code, and let's convert this into Python code inside of here. Oops, let's go into here. So let's paste in this code. Now, obviously, this is not going to work as is, but I'll show you kind of my thought process of how I convert this. So let's convert the comments into Python format comments. And then, okay, so what am I doing right here? So I am using the sign function to basically get this t value based on the current clock time and then multiplied by some frequency that I've set ahead of time. So in the Arduino code, I saved this frequency as an attribute on the class. So in the MicroPython code, I probably want to take in a frequency parameter to my initializer and then save that on my class. So now when I create an instance of the glow animation, I need to tell it what frequency it should run at. It's going to save that on this self.frequency object. And so now I can reference it in my functions here with this self.frequency. So this is going to reference this frequency that was set ahead of time right here. Now this pi variable and the sign function, I need to import the math module to get these, because in Python, these come in a certain module that you have to import. So math.sign or sin will give you the sign function. And then they luckily have a math.pi, but it's lowercase pi, that's defined for me ahead of time. So I'll do that. And then, okay, so now this, oh, and the other thing is that I don't need this float type right here, because again, in Python, it's dynamic. I don't need to specify types ahead of time. I can just tell it, make a t variable and set it to the value of this sign function that I'm going to call. And if it gets a floating point value back, it'll store that. If for some reason the math.sign function returned a string, it would store that also. So it's dynamic. It's happy to store whatever. Okay, so the last thing that I need to figure out is this clock. So I need a reference to my current clock. Now in the Arduino code, I stored this as a property on each of the animation base class objects. And then in my main Arduino sketch, I went through and set all of these values in the setup function. But really all that I need is a global variable somewhere that's an instance of my clock object that my animations can get to. And so what I did actually in my main.py, in the animations module, I actually just made a global variable called clock, and I set it in my main.py to an instance of the clock object that I created ahead of time right here. So I can do that in Python, because the cool thing is each module can have global variables, And Python's very good about namespacing so that you could have multiple .py files all with global variables that have the exact same names. And as long as you're smart about how you import those modules, they're not going to override. They're not going to conflict each other. Whereas it's a little bit trickier sometimes in the C and C++ world to do that. Okay, so let's create a clock global. And I'm just going to set it to none because I'm basically saying that, hey, there's a global variable called clock. I don't know what the value is right now, but my main.py is going to set this later. So that's what I can do. And so then that way, now I can just say, okay, give me the current seconds from my clock object. And I just want to double check that that's what I called it. So yeah, the current seconds on this object. So that's what I'm setting here. And notice I changed from this, oops, I just lost a battery on that light. Anyways, notice I changed from this syntax, this kind of arrow pointer, to the dot syntax. That's just in the C and C++ world. On this animation object, I'm actually storing a pointer to a clock object. That's what this star means. And when I reference a pointer, I actually have to dereference it. And that's what this kind of arrow operator does. It says, okay, this colors object is not an instance of the colors class. It's a pointer to an instance of the colors class. And so I need to dereference this. Again, this is C and C++ junk that you don't need to worry about in the Python world. It's kind of nice in that there is no concept of references to objects. Everything in Python actually is a reference technically to an object. So, but you don't need to worry about that because all I need to worry about is that there's this global clock object, and I'm going to set it to an instance of the reactor.py clock class, which I know has the current time in seconds, this current s value inside of it. So, okay, so that's fine. Now the next line, I'm going to do the same thing. I don't need to specify the type. And now I need this global colors object. So again, let's set colors equals none on here. And I don't need to do that pointer dereferencing junk. And then on my colors class, remember, it's going to be an instance of this gradient object. It has this interpolate function built into it. So I know that I can call that interpolate function and pass in the current value and then the range of values. That's what it's going to do here. And then same kind of thing here. I need a global pixels dot object on here. So pixels equals none, which my main is going to set ahead of time. And I should set, and so now I'm going to call the fill function on this pixels object. I'm going to pass it the color that it was just interpolated ahead of time right here. So this should be enough to implement the glow function. So let's try this out. Let's save this. Now in my main.py, I'm going to change things. So let's import animations 2, and let's call this as animations. Animations. So this just means that it's going to import animations2.py instead of animations.py. But when it imports animations2, it's going to rename it animations so that the rest of my code doesn't need to change. It's just going to use animations. And actually, I forgot, I called it fade instead of glows. So let's go back to animations2.py. Let's call this fade just to match up with what I had in here. Okay, now I haven't implemented yet the chase and the heartbeat and the sparkle and all of that. So let's just comment all of that out so that now my list of animations only has the fade animation in it right now. So let's save that. Now I'm going to plug in my CircuitPython board. So hey, we're over an hour into the stream, and now we're finally running some code here. But again, the point of the stream is I want to show how I've converted between these two types of code here. Now again, you're seeing this weird behavior, and that's because there's sometimes some noise on the USB line here, which sends it these spurious Control-C characters. But it's, so bear with me if you see some issues like that. Okay, so I plugged this thing in, and I'm going to look at the code in the Finder here. So here's my CircuitPython code. You can see here's this animations2.py file. If I look at my MicroPython board, I've already copied over the .mpy versions of all these files that I've created ahead of time. So let's copy over that animations2.py. And so I need to go back here, and let's grab animations2.py and my main.py. I want to make sure that I save these. Oh, I didn't save my animations2.py, so let's save that. Okay, so let's copy both those files over, and let's see. Yep, let's grab that, and then let's copy these onto my MicroPython board. And I want to replace those files. And okay, so just copy that file over, and it looks like it might not be working, or at least it's not running. So let's see if I got an error. Let's open up the serial terminal. And let's press Control D. Okay, so it's running. Okay, so so I forgot to set something here correctly. So it's basically telling me, okay, in my main.py, in my animations2.py line 19, so if I go to this, so this line failed. So this colors object, it's basically telling me none type has no attribute interpolate. So this colors is still set to none for some reason. And I think that's because if I go back to my main.py, I think I had changed the name. Yeah, so right here is where I'm setting this animations.color, which is actually looking in that animations module, and it's going to set whatever global variable is inside of there, but I called it colors instead of color. So let's change this to color, and let's change this to color. And now, again, I'll run into this problem where I've got a local variable that has the same name as an import or as a global variable right here. So that's kind of confusing. Let's put an underscore in front of there so that now it's more explicit that this is using the color global, and then this is making a local variable called color. Okay, so let's save that. And then I should be able to just copy over my animations2.py to change that. Okay, so I replaced that, and now, there we go. You see, it actually just started running. That's because whenever I copy a file over, it's in that auto reset mode, so it automatically started up my main.py again. So this is cool. You can see it's running the glow animation. This is, you know, if I press the right button, it's trying to cycle through the animations, but all I've got is glow defined right now because, you know, if I go back to that main.py, you can see my list of animations only has, or the fade animation rather is what I called it inside of there. So, okay, so let's do the chase animation next. So let's do, oh, funny, I have a semicolon after these and it seems like it's still working. That's weird. That shouldn't work. That should be an error. MicroPython must be ignoring that. That's very interesting that it's doing that. You know, I just want to be super sure that it's importing my animations the way that I expected here. So I'm going to delete the animations.mpy because I have a sneaking suspicion that maybe, well, no, it is because it found the error in animation2.mpy. But just to be sure, I'm going to delete this from my board so there's no way that it's using the old animations from here. Yep, delete that. Okay, cool. Anyways, okay, so let's keep going. So let's make let's do the glow animation, and I think this will be the last one. We're about an hour 20 into this, so we'll do this one, and then maybe I'll walk through the code for the others real fast, because I do want to talk about a performance issue that I ran into that we'll see with this animation, actually. Okay, so again, this one has a frequency that's set ahead of time, so just like with my fade animation, I want to save that, and then I need to implement this update function again. So now, let's grab the Arduino code for this. So for my chase animation, here's the update function implementation. So let's copy that out and then let's paste it into here and let's fix up the spacing a little bit. Okay, oops, oh, that really messed it up. Let's go back. There we go, because you do need to get the correct number of spaces, so 4 spaces for an indent or a tab character, and Python and MicroPython are very particular about that. Okay, so I don't have types anymore, so I get rid of my type. So I have an n. This is set to my pixels object, the number of pixels, but remember, in my case, it's this .n attribute, because on my pixels class in the Reactor, I set that n as the total number of pixels. So it's just a change in how I've called these things, basically. You know, basically, and I don't even really need to do this because in the Arduino code, I was just calling that function once so that I didn't have to repeatedly call it and, you know, storing that value. But, you know, I've already got that value, so I'm just going to, well, nah, we'll keep it as is. You know, I'll do a direct port of this code. Okay, so now I've got a for loop, and the syntax for this changes a little bit. In Python, you know, in the C and C++ world, you basically create a variable, you tell it when to stop or when it should run. So when this I index variable is less than n, which is the total number of pixels, and then I tell it what to do at the end of each loop, like increment to the next value of I. In Python, it's a little bit simpler. You use the for I in range syntax, and you tell the range function how many things to loop through, like what's the maximum value that you want to loop up to. It won't include the maximum value. So in this case, I want that n value for this. So that's what a for loop looks like in Python versus the same for loop in Arduino C and C++ style code. So that's what I want there. And I don't need this curly brace anymore because you don't need that in Python. Okay, so now I'm computing the phase. And again, I don't need to know the type of that thing. I just know there's a phase variable that I'm saving here. In the Arduino code, I was very explicit about casting to floating point types. In Arduino, or in Python and MicroPython code, numeric types can be either a floating point or an integer. You don't need to know or care about that. So I don't need to do this type casting anymore. My code can be much simpler. So my code here is just saying, okay, figure out the phase, which is basically how I want to offset each of these pixels so that each pixel is offset by a slightly higher phase than the previous pixel. And that's what makes it kind of do that chasing animation, because the sine waves are offset in time based on that. But anyways, so I'm basically just computing this phase based on the total number of pixels and kind of where I fit within that pixel range. And so now I need to change this to math.py just to match from the math module. Get rid of that trailing semicolon, which I'm going to do for all of these since I forgot it last time. Okay, so that seems fine. Now the next line, let's get rid of that type. And I'm going to call the math.sine function now. And I'm going to do 2 times math.py times the frequency times my clock current seconds plus the phase value that we computed ahead of time. And so the big difference between glow and fade is that in fade, I compute this color once and set all of the pixels to it, whereas in glow, I compute per pixel the sine wave value or the color value based on this sine wave. And so that's why I have to loop through each of these pixels, because the phase differs for each of the pixels. And so then I set the color of the pixel based on that phase value, or I have to recompute the sine wave value because the phase changes for this, because I'm adding that phase to it. So that's why I have to call sine for every pixel inside of here. Now the next code is going to be really similar to the fade function up here. I'm just going to grab I'm going to interpolate the color. So we'll do that, and it's not called colors anymore, it's called color. So I do that interpolation, and then I set the pixel color. So in this case, so now things change a little bit. So the typical way to set a neopixel color would be something like this. So I'd set it to, my color value, where basically I index into my pixels object. I tell it which neopixel to set, like pixel 0, pixel 1, pixel 2. And remember that pixels object gives me a global view of both the inner and the outer rings. And it looks like my camera's having some problems focusing on you. Let me just zoom out a little bit. Maybe it'll refocus. It's so bright that it's not focusing very well, but hey, you get a nice light show up there. Anyways, though, I'm indexing into there and setting this to the interpolated color, because if I go back to the colors.py, this interpolate function returns that RGB tuple or tuple value inside of here. So that's how I set the color basically for a single pixel in this case. So okay, so let's save this as animations2.py, and then let's also update my main.py, and let's uncomment this chase animation right here. So let's uncomment this, and then I need to make sure that I close that animations list properly. Okay, so now let's copy over this code again, and let's see what happens. I should have a second animation that should be able to work on this board. So let's copy animations2.py and main.py over. Let's see what happens. So let's copy these onto my board. Replace, and hopefully it works. Okay, it looks like something failed, so I must have messed something up. So let's open the REPL. Okay, so it's actually telling me, so I had my REPL, my serial REPL open already, and you can kind of see it detected that my file changed, and it ran main.py. Okay, line 35, the chase, it's telling me the module object has no attribute chase. So let's see it. This might have been when it was copying the files. It probably copied the main.py file first, and then it copied animations2.py. So what I'm going to do is I'm going to press Control D. D is in dog. That's going to reset my board. Okay, so it really is a problem here. So all right, let's debug this then. Let's see. So line 35. So animations.chase. So it's not finding this. Oh, that's, again, I screwed it up and I renamed this. So I didn't call it glow. I called it chase in my old code. So okay, we'll call this chase. No, actually, I really did screw that up. Yeah, this was supposed to be called chase. So sorry if you're watching and screaming, no, it's not glow, it's chase. Okay, so I'll save this and I will recopy this file over, and let's, hopefully this should, fingers crossed, magically work after I copy it. There we go. Okay, so it started up, main.py is running. Now if I press this button, we see, uh-oh, something happened. It's, let's see. Oh, okay, so something's wrong. So frequency is not defined. So, notice here, I'll reset the board actually, just so you can see. This is a good way to learn how to debug CircuitPython and MicroPython code. So I have my REPL open, the serial REPL. I just press Control D to restart. It just ran main.py. I'm going to press the button to switch animation. And now you can see there's my output. So it just errored out and it said frequency is not defined. So my animations 2.py. And I know the error here, actually, I just remembered it. So it's this line. It's kind of nice telling me line 31. So I can look in my editor. Here's line 31. And this frequency is not defined. Well, that's because in Python with classes, for when you want to reference an attribute of a class inside of the functions, you have to reference it off of that self object. So it's self.frequency that I need instead of just frequency. So a little bit of a gotcha in the porting of the code over there. Okay, so let's copy this file over again. And third time should hopefully be the charm. Okay, so it's running again. I will press this button. And there we go. So now it's running the chase animation. But notice that is not a very fast chase. Actually, mine's running, my Arduino is running the chase animation. Look at how much smoother the Arduino chase is versus this chase. This chase is kind of chunkier. It's basically, it's not updating at the same refresh rate. And unfortunately, this is kind of running into some performance problems, which are going to be common between Arduino and MicroPython, CircuitPython style code, because the simplicity of this function is great in that this is like less than 10 lines of code, and this has all of my chase logic implemented in it. But there are some things that are happening that you might not realize here, like this color.interpolate function is creating a new object every time it's called. It's creating this tuple object that has a red, green, blue color value. And every time it creates an object in MicroPython, it has to go find memory on the heap. And if it can't find memory, this garbage collection process has to run to go see which memory is not being used, reclaim it, and then grab some of that memory to give you, just so that it can make this little tuple object. And when you're doing something very, very quickly over and over, like I'm lighting up all 34 of these pixels over and over and over as fast as I can, every single time it's computing a pixel color, it has to go and create a new object, which might mean the garbage collector has to run. And so that's some of this overhead and some of this slowdown that you see, and why you can't get as fast of a refresh rate, because all of these objects and things are being created internally that you might not realize. Now, there are other performance problems too. All of the nice generic number types in Python, the fact that a number can be either a floating point value or an integer is great, but you lose some performance there because you might be getting floating point math where you don't expect it. So you don't have as much control, whereas in the C and C++ code, the Arduino code, because I'm telling it the type of every number, it knows, okay, if this is an integer number, I can do fast integer math. Whereas if this is a floating point number, I might have to do a little bit slower floating point math. In Python, it just knows this is a number. And if in some cases it's optimized to know if it's a float versus an integer. But it's in some cases you might actually get a floating point value where you really just wanted integers, and you're going to get slower math because of that. Now I'll show you, I fixed some of this performance issue by trying to get rid of that tuple allocation. So in my color, in my interpolate function, right here is where I create this new tuple object every time interpolate is called. And that's just because in the NeoPixel class, when you set a neopixel, when you set the color of a pixel, you have to pass it a tuple. And you have to construct a tuple because tuples are immutable. You can't change them. I can't just make a tuple buffer and then update the values inside of there. And so that's kind of a problem. So what I did was I added a new function to the NeoPixel library, and it's included in this sketch or this CircuitPython code, but it's not in the main NeoPixel library yet. And maybe we'll add it eventually because this is going to be a handy function. But basically, I made a setPixelRGB because the NeoPixel class, all that it's really doing is just updating this byte buffer. There's just a buffer of the RGB pixel memory, and it just blasts out that buffer of memory using the special timing of the neopixels. But whenever I want to set the color of a pixel, it's just going into this byte array and changing the byte values. So sure, it's nice to add these fancy tuple-based functions where you can very cleanly set the colors. I mean, notice this is how I'm setting the color. I'm just indexing into that list of pixels and I'm setting it to a tuple of colors. Real simple and easy and clean Python code, but it's not performant. And so that's why I created this setPixelRGB function where instead of taking a tuple in, I take in the red, the green, and the blue pixel bytes explicitly. So these are values from 0 to 255. And I just index into my pixel buffer, and then based on the byte ordering, because neopixels usually go green, red, blue instead of red, green, blue, and don't worry about that complexity, but that's what this math is doing right here. But I'm just looking into, okay, let's take this red value and set that byte directly so that I don't need to go and create this tuple object. I don't need to go and create, all of this, go find all these values in memory and, things like that. I can just have them passed into me, and a byte is a byte, and I'm just going to set that byte inside of my buffer and be done with it. So this is a trade-off. The code is less clear. It's not as nice. Now I have to call setPixelRGB, and I can't pass it a tuple. I have to pass it the red, green, blue values, but I'm not going to have to allocate that tuple anymore, so it's going to be a little bit faster. And so that's what I did in my main animation code. So let's actually switch back now. I'll actually show you this animations.py. So, here's the fade code, which is pretty much exactly the same as what we saw before. I'm just not creating that intermediate color object. But here you can see my code is now different for that chase animation. So, instead of setting, and actually I did a couple extra optimizations here too. So notice I pulled out some common factors. So if I go back to animations2.py, notice I'm computing the phase every single cycle, and I'm computing this, time value here, but some of the values inside of here never change. Like this n-1 times 2 times math.py, this is the same value for every iteration of this loop. It's only this I value that changes. And MicroPython is not smart enough, as far as I know, to realize that this never changes, so it can put it into a variable and just not recompute it. So I actually went and computed it ahead of time, and I call it this phase scale, 2 times math.py divided by the number of pixels. And then I can compute it here. Basically, I take my I times that phase scale value, and that's what I'm doing right here to get this new phase value for this. So basically, I'm doing this optimization ahead of time. So again, this is another little performance optimization to think about as you move into the MicroPython and CircuitPython world, because you don't have a compiler that's smart enough to do this for you yet. At least as far as I know. I think desktop Python, depending on the implementation, might be smart enough to do this kind of optimization for you. I know some of the just-in-time compilers like Pipe, I think it's, PyPA or whatever, it might do some of these crazy optimizations, like, they're pretty impressive. But hey, MicroPython, this is running on a little 48 megahertz CPU, so it's pretty darn impressive that any of this can run at all. But this is, again, a performance optimization. So I looked at what is a value that doesn't change within my loop, and I computed it outside of the loop. So I just did it once, so I don't have to recompute this every time. And then I recompute just based on the variables that change, which is just that I value right there. So that's what I'm doing there. Same thing for the sine function. There are some parameters inside of here that don't change. So 2 times math.py times frequency. This stuff never changes. Actually, times your current clock cycle. This actually never changes with each loop iteration. It's only this plus the phase that changes. My phase changes. So I can just compute this value ahead of time, save it, and then just do that single operation, which is exactly what I do right here, times, actually, do I do this? Oh yeah, so right here you can see I do sine scale. You know, I guess I could do another extra little optimization here. So hey, we're optimizing as we go here, because my clock's not going to change during the this loop iteration. So you know, basically I should just say maybe sine. It's not really scaling this anymore. So let's call this sine intermediate, and then so it's basically my intermediate sine value plus my phase that I'm computing here for that. So that's what I can do here. And now here's the big thing. So now I'm calling that set pixel RGB function instead of doing this pixel tuple set call. So right here, I'm not creating a tuple object. I'm actually calling set pixel RGB. And then I made this interpolate component function so that on my color class, instead of calling interpolate, which gives me back a tuple, I basically call interpolate component where I say, okay, give me just, you know, the red or the green or the blue component of my RGB color, and that's what the C value. So if I pass 0, I get the red component. If I pass 1, I get the green component. If I pass 2, I get the blue component. So that I can call interpolate component 3 times to get my interpolated RGB color value, but I don't have to get it back as a tuple object. So it doesn't have to allocate a new tuple object in this case, which saves on that memory usage. And so that's what's happening here is I'm calling set pixel RGB, and then I'm just passing it in, you know, the red interpolated color value, the green interpolated color value, the blue interpolated color value. And so that saves on that little memory optimization there. So that's what's happening here. And that's why, you know, let's change. So, you know, notice how slow and chunky that glow animation is. And then let's save, let's go back and we'll recopy the animation.py file over to our board. So let's go to here. Oh, actually, and I need to update my main.py. So sorry, let's go back to my main.py. And here it is. And so now, instead of importing animations 2, let's just import animations again. So now I'm going to get my optimized code. So I'm going to save that. And so now I want to copy over animations.mpy again, so that I've got that on the board. And then I also want to copy my main.py over again. So let's copy this over. And so now we should hopefully see, after it copies it, okay, so it's running again. Now we'll switch to the next animation. And hey, check that out. So it's a little bit faster. It's still a little chunky, but if you go back in the video, you'll notice that there was a noticeable performance savings to doing that optimization. So, you know, it just gave me that little extra speed boost. And hey, let's see what happens. You know, I just made that little factor change. So let's see. I'm curious to see what happens after I factored out the clock multiplication to do outside of the main loop. Who knows? This might make it a little bit smoother. So I saved this file. Let's generate the MPY file for this. So I'm going to exit out of this. I'm going to use the MPY cross tool, which I've got somewhere in my scroll back here. Yeah, here we go. So basically, the MPY cross tool, if you download the CircuitPython repository, you build the MPY cross tool. I've looked at the MicroPython guide, how to build the MicroPython source, and I talk about this MPY cross tool, or frozen modules. I talk about this in the frozen module guide also. Anyways, let's generate the MPY file from that animation. That's because I need to be inside of the power reactor CircuitPython directory. Now if I run this file, oh boy, come on, what's inside of here? It's called animations.py. There we go. Okay, so that just generated a new .mpy file, and you'll notice the time just changed to the current time, which is 8:45. It's a little bit late at night. Friday night hacking. I got to get ready for Comic-Con tomorrow. Emerald City Comic-Con. Hey, this thing, it's still running. I'm just got to double check. This is the longest I've run this thing, so I'm kind of curious how the battery life is. Okay, so let's copy this updated animations.mpy over, and let's see what happens. So it's, okay, so it's running. So now I'll switch it over. Okay, I think it's a teeny bit faster. You know, it's when I look at it, it's still a teeny bit chunkier compared to the Arduino code, which is actually running right now. It's very convenient that it's doing that. You know, the Arduino code is just that little bit smoother. Like when I look at it with my eye, I can tell that it's still not as fast. But on the camera, on the video, it's actually looking pretty smooth. And I think that's just because the refresh rate of the camera is a little bit different here. So, okay, I think I'm going to wrap this up. This was a kind of long video. But again, I wanted to kind of show a cool project. This is a pretty neat arc reactor project here. But I really wanted to show a real example of Arduino to CircuitPython, MicroPython sketch, something non-trivial. So, you know, this thing has a bunch of different modes, a bunch of different animations, and looking at what are some of the issues and things you're going to run into, like performance, and how to potentially mitigate some of those problems. So, you know, memory usage is going to be kind of the bane of your existence with MicroPython and CircuitPython. So you're going to have to do certain tricks like using the MPY cross tool to compile or generate MicroPython bytecode to save on the space, because you're going to get to a point where your Python source code, you know, these source files are just so big, it can't be parsed by the little CPU on your board. You've got to do that ahead of time on your computer with the MPY cross tool. That's what I just did with an animations.py file, that command I just ran. And then the other thing is, anytime that you're allocating memory, you're going to be potentially hitting the garbage collection, which is going to be a perf hit. And you might not even realize that beautiful syntax in Python is allocating memory behind the scenes. Things like using tuples. You know, anytime a new object is created, you can potentially run into some perf issues. So that's where a lot of your optimizations in MicroPython and CircuitPython are going to be, looking for those memory allocations inside of the loops and things. Because, you know, it doesn't really matter in this animation code. In my fade animation, I'm only calling this sine function once. I'm only getting this color once per cycle. That's not a big deal. But when I've got like 50 or 100 pixels, and every frame of animation I've got to go update each of those pixels, and if for each of those pixels I've got to do a bunch of memory allocations, that adds up, and that becomes a performance bottleneck. So, okay, I'm going to wrap the stream. If folks have questions, throw them in the chat, but I think that I've probably gone long enough that there are probably not too many questions. So we'll jump back to the main view. Let's see. Yep, let's go back there. So, yep, I think that's it. So thanks a lot for watching. If you enjoyed this, check out youtube.com/Adafruit. You'll see this video, all kinds of other fun project videos. Check out twitch.tv/Adafruit. That's where I like to stream these videos live. I usually do a live stream every Friday. And then you can tune in and see, you know, watch me do these things live, and watch my cat in the background there. She's sleeping in the box right there above my thumb. That is a cat, a real live cat on the internet. Anyways, so tune in, click the like or the comment or the subscribe on this video. Let us know that this is good content. We'll keep making cool stuff like this. And if you're at Emerald City Comic-Con tomorrow, that's March 4th, 2017, in Seattle, Washington, then you might see me with this arc reactor. And I will be wearing this arc reactor, the CircuitPython arc reactor. That will be the one that will be under my shirt, although I conveniently have a backup Circuit Playground based one. So anyways, this is Tony from Adafruit, Tony Stark this time from Adafruit. This is a little bit of a collaboration between Stark Industries and Adafruit Industries. So maybe we'll see more collaborations between Stark Industries in the future and Adafruit. So until next time, thanks a lot for watching. I'll see you guys later. Bye.